Hi everyone. This is going to be take number 2 of my presentation on how to increase efficiency and accuracy with the MOS system. Unfortunately, I forgot to press record earlier, so here we are again. I'm just going to begin by introducing myself. So, my name is Francis Nepveu. Everybody just calls me Frank. I'm a graduate of the Civil and Mining Engineering Technologies program at Collège Boréal. After graduating, I started working for NSS, which was about 7 years ago. I started off as a technical support and training representative, training everybody on like geosystems products, drones, laser scanners, stuff like that. I then moved on to managing our technical support and training team. And now I'm an account manager for our MOS system. So I handle projects related to MOS, such as implementations, trials, demonstrations, and any support and training as well. So I keep saying MOS, MOS this, MOS that. What is MOS? MOS is just short for Miner Operated Survey System. It's a computerized survey system which consists of a rugged tablet computer which controls a robotic total station. The tablet's loaded with the mine design for all of the levels in the mine, and then this gets laid out by the total station. It's primarily used underground by miners. We can, give the miner a paint pole or something like that, and then he'd be able to use the MOS system to mark up his whole entire face without any need for any mechanized equipment. But depending on the mine site, they're still going to need like a mine cat or something to go up to the face to be able to mark up all the bootlegs, to scale, to wash the face and all that stuff. So we have some dedicated survey functions, some tools that are specifically built for underground surveying, such as marking up rings or for picking up boreholes and stuff like that. We also have short-term planning tools that you can use to flesh out like a stick diagram for your long-term planning. These tools are also used to trace the mine designs imported from other planning packages. We have a ton of tools for long-hole design, and then we also have 3 different ways that we can map structures, veins, and stuff like that for geology face and back mapping. Let's look at a couple different ways that we can increase efficiency using the MOS system. So a survey for every face. With the MOS system, we're getting 2 birds stoned at once. Not only does it help you mark up, it's also recording a bunch of measurements while the miner is marking up. This provides a complete pickup of the face. This also includes, face profiles, which are good for calculating volumes, floor and a back shot, some topes, and we can also set it to capture a point cloud of the face, of every round. This could be pretty handy if you're planning on shotcreting your drift. We can scan before and after and then determine the thickness of the shotcrete that way. Having said all that, though, the objective here is not to replace surveyors. Don't assume that just because you've implemented the MOS system at your mine site that you're going to be able to gut your survey department. Instead, what we're trying to do here is we're trying to give your surveyors more time to perform more tasks that are critical to their job, such as a check survey or a cavity monitoring survey. An example of this would be one of the mines that we've worked with in the past. They've switched their production method over to long hole exclusively, and this requires their survey team to perform a lot of cavity monitoring surveys. This has consumed all of their time for the past 2 months. This was a while ago, but they've been so busy with all these cavity monitoring surveys that they have not had the time to go do a pickup. So they were able to just leave the MOS system unattended for that duration of time, and luckily they never missed a pickup, which was great. So for supervision, so we're giving supervision more oversight. It's easier for them now to see what went wrong and what went well. There's no more waiting for updated prints or drawings. Plans on the tablets are always up to date. Depending on the size of the mine and the size of the survey team, it can be pretty hard for the surveyors to visit every heading or workplace to do the pickup. This means that drawings can take a while to be updated, which also means that errors can go unnoticed for a while. An example like this one right here, you can see this round is just starting to go off the rails. And then the round right after it is already in the bush now. And then you can see that this third round here, they're finally reacting and trying to get that drift back online. With the MOS system, you're able to see what the, rounds that are being picked up day by day or shift by shift, depending on how quickly you're cycling rounds. This could also allow your shifter, your mine captain, your general foreman to notice any errors that are in the making much sooner, and at which point they're going to be able to go in and reinforce good practices and suggest ways on how to get things back online. The driller, shifter, general foreman, whoever's monitoring things, they can react faster and course correct anytime they notice that the drift is heading into the bush. And due to the wealth of information that is provided by the MOS system, we can kind of interpret what's going wrong, what mistakes are being made by the drillers, and then we can bring it up to them. And then, this ties into continuous improvement. Mining the design. So anytime we're designing any drifts in MOS, a lot of the mine's design specifications are tagged as an attribute to the center line. This means dimensions, grades, blast patterns, stuff like that. And this is to ensure that markups are accurate. When marking up a hole pattern, MOS can either use a predefined pattern, or we can use a pattern that's been designed by your explosives manufacturer, such as Orca or a Dyno Nobel. Either that, or we could plug in some general parameters of our choosing, and then MOS can use those parameters to design the templates on the fly. MOS also takes into account the as-built conditions and can detect where the design walls should be when designing the whole pattern. If the drift is turning, it's going to be able to fan all the holes on the inside wall accordingly, and then it's going to add a bunch of short holes on the outside wall. Or if there's an intersection or passing lane that's coming up, MOS is going to be able to add some holes to whatever side is needed and then fan those holes to open things up. Say your mine has Wi-Fi available at the face, we'd be able to transfer data in close enough to real time. Any design changes that are made on surface can be sent directly to the tablet, and once the markup's complete, that information gets sent back to surface onto the server where the staff in the office is able to start processing it. A scenario where this could be pretty handy is, say a miner is going to see the planners for an updated print, but the planner's not quite done. They tell the miner to head underground and get started, and then they'll call them on the radio once the print's ready. So once they call them, the miner just has to turn the tablet on, say they're connected to Wi-Fi at the face, or just go to the nearest hotspot, sync the tablet, and boom, an updated print. The miner can then go finish his markup, and as soon as he presses save, it's going to sync right back to the surfer on surface. Otherwise, we can store the tablets in the refuge station, say Ethernet is available in the refuge, and the miner would just pick up the tablet at the beginning of the day from the refuge and bring it back there when he's done. Or worst case, you take the tablet from surface and you bring it underground with you and bring it back once you're done your shift. Let's look at a couple different ways that we're increasing accuracy using the MOS system process. So this process is the meat and potatoes of the MOS system, and it incorporates over 20 years of feedback from drillers. The markup process is quick and efficient. It takes me longer to explain it to people than it actually does to mark up a face. Process takes around 15 to 20-ish minutes to complete, and then if you put it in the hands of a competent miner or somebody that's very experienced, it can take them less than 10 minutes to complete. 2-point triangulation. So this is the first step when marking up. Once the total station is set up, we use a 2-point triangulation, also known as a resection, to set up off of the existing survey control network, which was set up by the surveyors. The miner can then set up anywhere in the drift. He's not forced to set up underneath a plumb bob or a wall bar. He can hug one of the walls in case there's equipment in the way or if the drift is turning. The MOS comes built in with a tolerance of 25 millimeters for setups. So this ensures that setup errors don't add up in the long run. If the error is greater than 25 millimeters, the miner cannot continue. Face profiles. So we measure a face profile for every round. Basically what the miner does is he's going to trace the laser on the face, on the walls, on the back, and on the floor, maybe about a foot away from the face, and then it's going to become very apparent in the next few slides why face profiles are very useful. Centerline. So during the centerline step, the instrument's going to automatically turn to the center line of the face and start blinking, and then the miner just has to paint across where the laser is pointed. The center line is always going to be staked out with an accuracy that is always greater than a centimeter, regardless of how far away the face is from the instrument or where the instrument is set up in the drift. Other conventional methods tend to lose a lot of their accuracy the further away the face is. Typically, we mark it up at around 1.5 meters above the floor. This will give the miner the first indication as to whether or not the drift is online or if he's walking into a jackpot. So say the center line is too close to the floor, then that means the floor is too high. Or if it's too high on the face, then that means that the floor is too low, or the back might be too high. Overbreak and underbreak profiles, very handy. So once the center line is located, MOS will superimpose the face profile that was measured in the previous step over the design profile. This is going to give the miner a clear indication as to whether or not the floor, the floor and back is too high or too low, or if the walls are too wide or too tight. This overbreak underbreak profile is displayed for every face that gets marked up. This helps the miner decide what he has to do to ensure that the drift stays online. Once the center line is located, MOS will superimpose the face profile that was measured in the previous step over the design profile. This overbreak and underbreak profile is displayed for every face that gets marked up. This helps the miner decide what he has to do to ensure that the drift stays online. This step also kind of turns marking up into a game for some of the guys. When we were on site training, we'd often overhear the guys bragging in the morning in the huddle that oh, I had a 5% overbroken round, and then the other guy'd be like, no way, I had a 3.5% overbreak on my round yesterday, right? So it kind of keeps the guys more involved. It gives them more of a sense of pride in their work, and they get you know, a better picture of what's going on. Just like the center line, during this step, the total station is automatically going to turn and trace the grade line on the walls. The miner just has to chase the laser with a can of paint, kind of like a cat chasing a laser pointer. Once the laser reaches where the design wall should be, it will pause to blink so that the miner can mark that up. From there, it's going to trace a line on the walls that is on grade. So the jumpman can reliably line up their booms with this line, and they're going to be drilling at the correct grade. As mentioned before, MOS can either use a predefined template or a template that's generated on the fly based on your parameters. MOS then lines up this template with the face to generate the collar locations, and then projects it forward the length of the round to generate the total hole. Once the pattern is fully generated, the total station just turns to all the different collar locations. It'll stop and blink, and then the miner just has to mark that up. We also have an option to export the pattern in an iReadies format, which a robotic jumbo can read. You just have to save the pattern to a USB stick and then plug that directly into the jumbo's computer. MOS at the moment cannot position a jumbo along a tunnel line, so this is only recommended when using the bit navigation method, which is calibrated by lining up one of the booms with the center line and a backside. So how does MOS compare to other conventional methods? The conventional methods that I've seen the most of are chains and washers, drift scopes, and the monopod system. When training, I always get the same comment from the miners. You know, I take too long sometimes to explain things properly, so they always tell me that, oh, I could have had my center line marked up and everything marked up by now. So what I'll usually do is I'll have a shootout against them. They'll set up their monopod, let's say, and then I'll set up my MOS system, and then usually by the time that they found their center line, I'm done my complete markup, so grade line, crank line, my whole entire hole pattern, my backsides, everything. So the monopod systems, there's a couple disadvantages to using that system in comparison to the MOS system. The system tends to lose a lot of its accuracy the further away it is from the face. This is just because, you know, sometimes it's hard to turn the exact angle that's indicated on your print. A lot of these theodolites don't always have an EDM, electronic distance measurement. So what miners have to do is they either have to pull a tape or use a laser distance meter to find out how far the face is, which can also introduce some added error. Chains plus washers and drift scopes are negatively affected by the ventilation. When you're using a drift scope, the ventilation causes the drift scope to swing wildly, so you kind of have to guess where the center line is. And then all of these systems need to be constantly updated by the survey department. With the MOS system, the surveyors would only have to step in case there's a huge discrepancy that gets noticed. Let's look at some other functions that are included in the MOS system that also help to boost efficiency. One of the most stressful times in a surveyor's life is at the end of every month, when everything that has been mined in the last 30 days has to be reconciled. One method that's pretty common with calculating your month's end volume is called a cubic assessment. So here's an example of a cubic assessment. The The way it works is you force your wall struts up and down to the elevations of the back and the floor, and then from those two lines you're able to create a solid. The disadvantages of this method is that it can't distinguish if the back is arched or if your shoulders are arched, and this tends to add a lot of material in the shoulders, which can skew your results. A better approach is to use face profiles to generate your solid. Right here we have an example of that. This will provide a much more organic looking solid that is a much better representation of what the volume actually is. If we were to overlap the cubic assessment over our Moss solid, you can see that there's a lot of additional material that gets added to your month-end calculation. Our Geology face mapping tool comes in 3 flavors. You can either use a total station to measure all your structures, digitize directly on the tablet, or you can bring a piece of paper, scan it, and then digitize afterwards in Moss. Using the total station is obviously going to offer the highest accuracy. The geologists would utilize the existing survey control network that the miners and the surveyors are setting up, and then they would just use the laser on the total station to trace out their structures. Otherwise, digitizing on the tablet or from a piece of paper can be improved by the fact that, and this is assuming that the miners are going to be using Moss in geology-driven drifts, so they're going to get a floor and a back shot whenever they mark up, and then what the geologists can do is they'll take that floor and that back shot, and then they're going to snap whatever it is they're drawing to those shots in order to, geo-reference everything quickly. If you're in the market for a dedicated cavity monitoring instrument, consider getting the Moss system instead. With the Moss system, we can turn any total station into a cavity monitoring instrument, providing it's compatible with the Moss system. You would only require a single instrument to perform the CMS. No need for a second instrument to shoot in the instrument that you put in the stope. Using joystick commands on the tablet, we can get the total station to perform a 3-point triangulation, also known as an unleveled setup, which will geo-reference your CMS in the field. You can either use your TS15, 16, your TS12, that lineup of instruments to produce rings or solids. This should take about 20 to 40 minutes depending on the resolution that you pick, or you can use a multi-station, so the MS50 or the MS60, which produce point clouds. Those are able to complete a scan within 6 to 12 minutes, again depending on the resolution that you pick. However, Leica in February of 2020, they released a new and improved MS60. This new MS60 should theoretically be able to perform the scans in under a minute. This is going to be thanks to the 30,000 points per second scan rate, as opposed to the 1,000 points per second scan rate that the old MS60 has. And also it uses a spiral scans pattern that also speeds things up quite significantly. The cost of Moss also includes a copy of an OEM version of AutoCAD. No need for a separate subscription or license. Tools that are included with the Moss system, you get your ramp design, your raise design, plotting tools, glass pattern design, borehole layout, drill hole locating, and then solid generation. Pretty much everything you need to flesh out a long-term stick diagram. The ramp layout tool in particular is very handy. You just need to enter some generic parameters such as the dimensions, grades, stuff like that, and then you click from one endpoint to another, and it's going to complete all the line work and the annotations that are required, and then all of that is going to be drawn in 3D. The Moss system has a very good long hole design and layout package. We are able to cut rings pretty quickly using either a cartwheel method or cutting them parallel to a vertical plane. Once all our rings are cut, we're able to use a bunch of tools to lay out where our holes are going to go. We can either fan them, make them parallel to the ore body, or we can draw them manually. Once all our holes are laid out, we're able to load them using our preferred parameters, and then using our plotting tools, we're able to prepare all the rings in their tables for printing. And then within an hour or so, we're going to be able to hand a fat stack of prints to our drillers so that they can go and get to work. So this is just going to be a little bit of housekeeping. I think this is going to be important to mention what is compatible with the Moss system. This is Leica Geosystem's current lineup of total stations. We have a TS13, the TS16, the TS60, and the MS60. Presently, the TS13 does not support Geocom, meaning that it is not compatible with the Moss system. For those reasons, we recommend either a TS16 or an MS60. Let's talk about backwards compatibility a bit. So if you have any of the following instruments shown in this slide, there's a possibility that they can be used with the MOS system. All of these robotic total stations must have an existing Geocom license in order to interface with the MOS system. Sometime in 2019, unfortunately, Leica decided to make it so you can't order a Geocom license for the TPS 1200 series or TS12 anymore. However, if they already have a Geocom license, you can still use them with the MOS system. The TS15 and the TS50 MS50, however, those you can still order a Geocom license, so those would still be considered compatible. It's still recommended to purchase a TS16 or an MS60, however, since these are going to be, as Leica likes to put it, future-proof. So they're still going to be supported, serviceable, and they're going to have a longer lifespan than any of the instruments in this slide. It's also worth mentioning at this time that MOS does not work with robotic total stations from other manufacturers, such as Trimble, Topcon, and Sokia. So how well does MOS play with other softwares? In my opinion, it plays pretty well with them. We consider MOS to be agnostic in a way where we're able to get it to work with your A-mines, your DESWIS, your mine sites. Doesn't really matter. Everything is AutoCAD based. We're using DWG files and DXF files, which are all compatible with any of your modern planning packages anyway. So one way that we can get things to work to tie in together is obviously you're going to have all your drawings from your planning package that are saved on the server. We're going to take these drawings off the server, put them on the tablet. We're going to do a little MOS trace in order to prepare those drawings for markup. Once we get any of our markups done, MOS is going to export some data that can be synced either using a OneDrive or a sync center back onto the server, which your planning package could then import in order to start post-processing. So with the increased efficiency and accuracy, how much money can we save? The MOS system has a proven track record in reducing overbreak, as can be seen in this example here. Here we have out of the 24 rounds, we have the highest overbroken round of 13.9%. Every other round in this drawing are around 10% or lower, which is really good. Here we have just a little return on investment calculation. Everything's calculated based off a width of 5 meters, a height of 5 meters, a length of 3.5, and then a specific gravity of 3.1, which is like the average specific gravity of an ultramafic rock. We're assuming that the overbreak is 25%, and we're trying to reduce the overbreak by 10%. And then our mining costs are around $120 per ton. And then a MOS package, assuming that we're only purchasing the single unit, is $88,000. So taking all these numbers into account, we're expecting that within 95 meters of development, we're going to be able to break even and get our, pay off our equipment. And then say we annually develop 2,000 meters, with a reduction of 10%, we're going to be saving $1.7 million. One of our customers, after purchasing 10 units, they were able to dial down their overbreak from an average of 27% down to an average of 17% in a 7-month period. So within that 7-month period, they were able to save all of that money that they had spent on the MOS system. If you have any questions, please feel free to reach out to me or reach out to us on any of our social media platforms. So we've been keeping a trend here at NSS of having a webinar every Wednesday. Next Wednesday, we're going to have a webinar on the hidden cost of mine incidents and how to save millions of dollars with the Hexagon safety products. This is going to be hosted by Victor Valdez. So please stay tuned for that. And thank you very much for your time.